So I understand that some students have the understanding of data science equal to programming. And whenever we are studying anything computer related, we must always go to programming. But in fact, when we are studying algorithm, okay, programming implementing the exact algorithm in a particular programming language is not always the main concern. Okay? 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 And in fact, okay, I am using my personal experience, okay? I was an undergraduate in a computer science major, okay, in another university, okay? And that university actually have the computer science department actually have a relatively high ranking in the world. Okay? And during my undergraduate study, when I was studying algorithms, okay, there is a dedicated course for algorithms. The whole course doesn't actually train you to program algorithms in Python or any other programming languages. Okay? Rather than that, it actually asks you to prove whether the algorithm has a specific time complexity or space complexity. Okay? Okay? So I understand that many students have a concern of this course is not as programming intensive as you believe to be. Okay, so I'm trying to explain once again. Okay, but anyway, I understand that it is relatively more easy to understand algorithm using programming code. And I also want to demonstrate all the algorithms we discussed in the lecture time can really be implemented. So I also included the programming code for solving the problem we discussed in the lectures, okay? But I am not going to really heavily emphasize on programming in the examinations. Okay, I hope you can understand. Okay, okay, this is the reality about algorithms in the field of data science and computer science. Okay, it is not just how Nanyang University works. Okay, in fact, other universities like CUHK or HKUST or Hong Kong University, HKU, their computer science major, they would not spend a lot of time to talk about how to write program, how to write algorithm into program in the algorithm course. Okay, the main focus is to educate students about how to prove an algorithm is within a specific time or space complexity, or how to analyze the performance of an algorithm, or how to design algorithm. Okay, and the algorithm design doesn't necessarily heavily attach to a learning of a specific programming languages. Okay, 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 okay. In fact, back in my days, okay, when I was an undergraduate, I learned Java in the first semester, and then I learned C in the second semester. And in the second year, I actually learned a lot more programming languages. Okay, so I hope students can, I hope everyone here can understand that programs training to be a good programmer for a specific programming languages is only half of the story. Okay, there are more things involved that about computer science or even data science. Okay, okay. I hope I get the message through. Okay, okay. So I understand that in the previous lectures, and also you can totally try to run it. Okay, in fact I can even run it right now. Okay, I can press the one over, and then you can see the code can really be executed. Okay, or we'll actually go through the code then. We'll actually go through the algorithm part in the later lectures. Okay, I only covered a bit, around half of it in the previous lecture, but I'll afraid the rest of the coding later. Okay, so as you can see here, all the coding can be executed. Okay, the depth search may actually be stuck in a loop in some situations. Okay, so but as you can see here, all the coding can be run. Okay, okay, so you can try at home. Okay, You can try to understand the coding and reading the lecture free on your own if you want to self-study, okay? All the materials are here, okay? So if you are interested, you can self-learn, okay? But if you want to get a better understanding, you can self-learn and then listen to my version of the interpretation in the lectures, okay? So any questions? Any questions? Any questions? Any questions? Any questions? Any questions? Okay, so let's get to the lecture part. Okay, so in the previous lecture, we actually go over the implementation of the successor function. Okay, and one thing I didn't do is to really use graph, okay, really use images or use diagram to explain what I'm actually doing with this whole pile of data structures. Okay. So in fact, what I'm actually trying to do with the successor function is something like this, okay? First, the top layer is a dictionary, okay? The reason why I'm using a dictionary is because a function is essentially a mapping between items of two domains, okay? 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 You should know this concept in mathematics that the core foundation definition of a function is a mapping of variables or mapping of values in two domains. So I am using dictionary because dictionary is essentially mapping of key and value that fit in the definition of a function the best. Okay, and also we are also working with a problem that the transitioning of the node to another node is essentially a hard-coded map. There is no reasoning involved. Okay? Because the transitioning between the states is just a fact. Okay? It is something that cannot be reasoned with and compute with. Okay? So instead of writing any kinds of algorithm trying to deduce the transitioning available, I'm using the simplest approach, okay? I'm actually using the hard coding, okay? I am using a dictionary to hard code the mapping between the state and the successor state, okay, and the actions, okay. And the reason why I do the hard coding is that there is nothing that I can compute, okay. Essentially, I am just following the established role network of Romanian, okay. So I am actually trying to represent the given any state, okay, what kinds of actions that the agent can do and the corresponding successor function in a mapping, okay? And this mapping can be written, can be implemented, or can be hard-coded in your code as a dictionary data structures, okay? Because dictionary is essentially mapping, so it matches the ground underlying principle of function, so that is why I use it, okay? And for the action next state or successor state pair, because a state can go to more than one state, so I am using a list. Okay, okay, because a state can move to more than one state, so I am using a list. Okay, so as you can see here, the CTO layers here is mapped to this data structure. Okay, to this list. Okay, so this list is storing where the agent can go to from all layers. Okay, okay, and in this list, each row, each entry, each entry is referring to a state that the agent can go to from all layers. Okay, okay. For the first list here, pointed by the ODS, okay. In the first list here, okay. This list is actually referring to the list of the states that the agent can travel to if it is not at ODS. Okay, and for each entry here, it is storing two values. The first value is actually the action, and the second value is the city that it will go to when the action is performed. And for the action, we just recall the starting point and the ending point on the transition, okay? Because we are going from ODS to series, okay? So because the ODS is connected to series, okay? So to go to ODS to series, you will need to take the action from ODS to series, okay? So the action will have two entries, that is ODS, that is the starting point, and the ending point series is the ending point, okay? And in the next stage, okay, that is noted, that is specified, the orange color, that will be the end position of the agent when the action is performed. And because we are going from ODS to series, so the endpoint is also series. Okay? Okay? So this is how the data structure is being implemented. Okay? Okay, so any questions? I hope this diagram can illustrate the essentially what all this coding is about. Okay, so any questions? Can you follow what I'm saying? Okay. So maybe there are many different ways to implement the mapping. Okay. I am using the simplest way. Okay. I am using the built-in data type that I have in Python to achieve the task. Okay. So if you are building object on your own, then you can make this even more beautiful. Okay. But I am just trying to get this problem done with the most simplest data type that I have in my hand, okay? In Python, okay? So this is why I implement in this manner, okay? But of course, you can totally use another way to represent the mapping, okay? Okay, there is no solid answer for this, okay? Okay. And for the step course, okay, for the Go test, you just check it whether it is booters, okay. So I don't go for it, okay. For the step course, what I am doing is something like this, okay. I am actually creating a two-layer nested dictionary, okay. In the first layer, I am taking the starting state as the key, and it will point to another dictionary, okay. And the other dictionary will contain the key will be the end state okay? And at the end, after the indexing of two dictionaries, okay, then we're able to point to the real step course. Okay, so this is what we are trying to do for the step course. We are just using a two-layer dictionary. The first layer dictionary is the key, is the starting state. Okay, it points to a dictionary that refers to the cities that the agent can go to from the starting point. For example, the city ODS in the first dictionary is pointing to a dictionary, okay? And this dictionary means that the cities that the agent can go to with ODS, okay? So, and then we key in the cities that the agent will arrive, okay? And we keep it series, okay? So at the end, we're able to get the course between the starting state and the end state, okay? So essentially, we use two layers of dictionary to refer to the mapping of the course of two cities, okay? Starting point city is the first key, and the ending point city is the second key. Okay? Okay. So any questions? Any questions? And in fact, you can also create an extra data structure, okay? Trying to join the first city and the second city as a data structure, and then you use it to be a single key for retrieving the course. Okay, you can totally do things in this manner. Then your data structure will be reduced to only one dictionary. Okay, but for the sake of simplicity, I am again using built-in data type to implement the step course. So that is why I am using two layers of dictionary to achieve the job, to do the job. Okay. But fundamentally, you can create data structure that create object that contains the starting state and the end state, and then you can do it with just one dictionary, okay? But that is for your own studies, okay? If you want, you can take my code and try to re-implement it such that we can do it with a single dictionary. But I'm here taking a more simple approach. Okay? Okay. So at the end of the day, if you go back to our coding implementation, you will see that we actually is packing the problem in a object called travel problem. Okay, in this travel problem, we actually define the initial state and the goal state, and we actually define the network structures of the problem in the state action result this data structure. Okay, and then we also define the step calls in a data structure like this. Okay, okay, and then we also implemented the successor function, the goal test function, and the step calls. Okay, and providing the successor function, the goal test, and the step calls, and the goals and the initial states, all these will already be necessary for the algorithm to perform its task. Okay, if you go to check out the search algorithm, okay, the algorithm used by the computer to solve the problem. If you take a look on the implementation, you can see that the implementation is completely separated from our problem. Okay, you cannot see any traces of coding here that refer back to our traveling problem. Okay, 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 and that is good because we are doing a action called separation of concern. Okay, I believe that you should learn this term when you are taking the object-oriented programming course, right? Right, right, right. You should have learned the separation of concern or isolation in your object-oriented programming course, right? Okay, so when you are working with object-oriented programming, okay, one of the key things we want to do is to try to separate try to organize our coding according to their purposes. Okay, we want to encapsulate things, okay, and encapsulate coding and data that is closely related to each other. Okay, and in this scenario, we are actually removing the problem definition implementation from our search algorithm implementation. Okay, this actually allow us to debug the problem separately. Okay, if there is coding error in the search algorithm, I just work on the search algorithm. If there is implementation error in the problem, I work on the problem. Okay, and the second beauty and the second important beauty of this approach is that if I am working on another problem, I just swap out the problem and then I can keep this section of the code relatively unchanged. Okay, okay, okay. So essentially, you can consider how we solve problem in this approach is that whenever we have a problem, we implement a object like this, okay, that essentially describe to the computer what is this problem supposed to be. Okay, and the computer will take over and then run the search algorithm to get to the results. Okay, so we being the programmer doesn't need to figure out a dedicated algorithm to solve a problem. We are essentially trying to convert our problem into a specific representation, that the computer can understand, and then we let the machine do the rest. Okay, so that is why that is considered to be AI in the 1970s and 1980s. Okay, So any questions? And you can see, you may notice this when you are looking at the code. All the coding we do here doesn't involve writing any algorithm to solve the problem. All the coding we have right here in the truffle problem, this object is just describing the problem itself. Okay, I hope you notice this. Okay, when you are reading the code here, I am just defining the network structure right here. I am just defining the step cost right here. And for the successor function and for the goal test here, I am just merely providing an interface for the algorithm to get to the data. Okay, so you can actually consider this whole travel problem is just a lump sum of data. Okay, it is just a lump sum of data. Okay, we do not write any coding to do any computing in the travel problem. Okay, but we are still able to solve the problem. Okay, and the reasoning is that once we can define the problem in the single state representation, the computer will handle the rest. Okay, so any questions? Essentially, this is just the same as when you are using ChatGPT, you would actually use some prompt to help you to get the ChatGPT more easily understand what you want to do. Okay, when you learn CCC 8015, maybe if you are taking the course right now, you may not know what I'm saying because that will be discussed at the later part of the course. Okay, when you have studied CCC 8015, okay, the generative AI, you actually learn a concept called prompt. Okay, instead of just giving my question to the ChatGPT using just natural human language, I can actually use some advanced prompt to help the ChatGPT perform its task even better. In fact, I am translating my prompt into a specific format that the ChatGPT really understands it better. Okay. And here we are doing substantially the same thing. You may see a lot of coding here, but what we are doing is we are converting our problem into a data format, data representation that the computer can understand. And the rest is that the computer will just run search algorithm to find the solution for us. Okay? Okay. So the beauty of this approach is that you don't need to design a specific algorithm to solve a specific problem. You are merely using coding to describe your problem. Okay? And then you let the computer to do the rest. If you take a look on the coding here, you can see no computing here. Okay? All these are data only. Okay? So any questions? Any questions? Any questions? I hope I can get my message full, okay? Okay. And now we have been talking a lot about how the AI, how we can formulate our problem into coding that the computer can understand. Then the next part is we need to describe the algorithms that the computer use to search the solution. Okay. Essentially, this is the algorithm basic flowchart. Okay, what it is trying to do is something it is shown in the flowchart. Okay, you may think that this flowchart is a little bit difficult to understand, and I will explain it with examples. Okay, and I will gradually explain different varieties of the search algorithms. Okay. Okay. So any questions up to now? And one thing I need to address, I need to explain, okay? Especially I consider nowadays many students will use the AI to help with their understanding and the studies. Okay. When we are talking about search algorithm in this course, ultimately we are talking about how to find a path in a state space graph. Okay, this is the nature of our search algorithm. Different a graph or a network, we find if there is a path between two nodes. Okay, okay, and in the data in the data structure field, okay, we can actually use a data structure called adjacent list or adjacent matrix to represent a network like this. Okay, and when we want to solve the problem of finding the path of two nodes, we can actually use algorithm like depth first search and breadth first search. Okay, and essentially we are using those same algorithm to solve our problem. Okay, but there is a slight difference in terminology. Okay, there is a slight difference in terminology. When we are trying to run a depth first search on a graph in the context of the data structure, you will actually run it over the whole graph. Okay, meaning that you will consider the whole graph as your input. Okay, but when we are using the graph algorithm approach to solve problem, there is another perspective. We are not interested to find whether a node is connected to all the nodes in the graph. We are interested to find a path that connects the initial state to the goal state. Okay, so when we are describing the algorithm, we are describing the algorithm under this perspective, that is finding a path from the starting point to the end point, okay, to the goal state. Okay, so once our algorithm reach the goal state, we will stop our algorithm. Okay, and that is rather different than how data structures perspective is on those algorithms. Okay, if you are studying those algorithms in the context of data structure, you will want to process the whole graph. Okay, but in the context of data problem solving in AI, we don't care about the whole graph. We only care where we can find a path starting from the initial state to the goal state. Because that is ultimately what we want to find in the first place. We want to solve the problem. And the problem solution is the sequence of action that allow us to go from the initial state to the goal state. Okay? So under this assumption or under these conditions, okay, under the condition of we just interested in finding a sequence of action that allow us to go to initial state to the goal state, the whole graph situation doesn't matter to us that much. Okay, we don't necessarily need to know whether initial state can travel to all the nodes in the graph in order for us to draw the conclusions. Okay, so our algorithm will stop right at the moment we find a path that allow us to go from the initial state to the goal state. Okay, and that will actually change how we conduct complexity analysis when we are discussing those algorithms. Okay, so you may find that the description on how this algorithm works will be different from the information you find in ChatGPT. Okay, Okay, you may find that the lecture notes is describing those search algorithms differently from the ChatGPT. Okay, okay. The reasoning is that we are taking different perspectives. Okay, this is something I need to discuss with you before we proceed. Because I understand that if I do not explain this in great detail, then someday you may take the ChatGPT generated output, okay? The ChatGPT description of those algorithms and ask me why, Professor, the things you talk about in the lecture is different from ChatGPT. Okay, and the reason is because we are taking different perspectives. Okay, okay. We are solving the problem of finding a path from the initial state to the goal state as a graph problem. So we are using depth first search and breadth first search, those algorithms for the sake of this, for the sake of finding the path connecting from the initial state to the goal state. Okay, but we are not interested to look at the whole graph. So the reasoning on the complexity analysis will be totally different. Okay? 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 I will need to discuss it in advance, okay? Because you actually totally perform the complexity analysis differently if you are taking these two different perspectives. Okay? So any questions? Any questions? Any questions? Any questions? Any questions? So if you are interested, you can also go to use ChatGPT or go to refer to data structure lecture notes. You can find the internet, okay? And you can find how data structures perspective is discussing those algorithms, okay? But I will not go into the details of that perspective, okay? Because we are not a data structure course. Okay? Okay. So let's get back to our problem. How the computer solve the problems, okay? Essentially, the whole idea of the flow of this flow chart is difficult to understand. So I will use example to explain, okay? So now we refer to our Romanian Turing problem, and this is the network shown below is the state diagram, okay? The state graph that we have already, the state space graph that we have, okay? And this graph is showing the connections, showing the available transition that you can have between different states or different cities, okay? And we start at A city, okay? So in the search tree, we'll put down the A city, okay? Before we talk about search tree, let's do a brief revision about trees, okay? I forgot about this, okay? So in case you also we don't recall what is tree, okay? So we will refer to what is tree first. So if you recall what you learned about trees, okay? A newcomer student will just randomly find it. If you recall what you learned about trees in data structure code, okay? So essentially, tree is a data structure that represents the hierarchical relationship between the entries, between the data elements. Okay? Okay. So this is so-called the hierarchy. Okay? Okay. The top node, okay? You in this diagram, this is showing the tree structures, okay? The top node that is called the root node, okay? The root node is the starting point of the tree data structure, okay? It is a node that doesn't have any parent nodes, okay? Okay, and in a tree structure, okay, a tree node may have parent node or children, okay? So when a tree node is having child node, it will look something like this, okay? It will have the nodes in purple color, okay? As you can see here, a root node can have different children node, okay? And we also consider them as branches, okay? And you may learn in the data structure called a binary tree, right? In binary tree, a node can have two child node, right? Right? Just to make sure we are aligned with the terminology, okay? So I will ask again, okay? So in the data structure course, have you learned a thing called binary tree? Binary tree, okay? Okay. And in binary tree, you should know that a node can have except the terminal node, okay? A node can have two node, right? That means the children node, right? Okay, then the child node, right? Okay. And in fact, binary tree is only one type of tree. There are many different kinds of trees available in the data structures. Okay. So you can have more than two children, more than two child node for a node. Okay, and in this diagram, the root node is having three different children nodes or child node. Okay, okay. This is something we need to establish first. Okay, or I understand that most of you have been learning the heap tree or the binary tree a lot, so you may have the assumption that every tree in the computer science or data science only have two children. But in fact, it depends on how you design the tree. Some tree can have more than in some trees, okay, a node can have more than one child, okay, may have more than two child node, okay. In this tree, we have three child node, okay, okay. This is the first assumption that I will need to correct. Okay, you may have learned binary tree or heap so much that you believe that a node in a tree should only have two child nodes, but in fact you have more than two child nodes. Okay, okay. And if a node is at the end and doesn't have any child node, and that node only has parent node, we call this a terminal node or a leaf node. Okay, okay. And we can also call part of a tree as a subtree. Okay? 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 Just to make sure you recall the terminologies. Okay? You can also call part of a tree as a subtree. Okay? Okay? And you can see in this diagram, I also labeled some numbers in green. And those are actually referring to the level or the depth of the node. Okay, so essentially it is referring to the distance from the root node. Okay, and as you can see here, the node here will need to go through is 3 nodes away from the root node. Okay, so 1, 2, and 3. Okay, so this node is 3 nodes away from the root node. So that is why its depth is 3. Okay, okay. The root node have a depth of 0 because the root node is the root node itself. Okay, so root node traveling root node is going back to itself. So the distance between the root node to the root node is 0. So the depth of the root node is 0. Okay, okay, okay. So any questions? Any questions? Any questions? Any questions? So this is the nature of the terminologies that we should use regarding trees. Okay? And in fact, okay, this is the binary tree. The tree at the left-hand side is called binary tree. And this is the tree that you learn in your data structure course. Okay? And I believe that most of you will believe that all the tree in the data science or computer science is look like this. Okay? But in fact, there are many different kinds of trees depending on your application. Okay? Maybe you will learn it, but you may not learn it. Okay? There is another type of tree called the B plus tree. Okay, the B plus tree is widely used in file system and database. Okay, that the usage of the B plus tree is to index the location of files or data records in a database. Okay, and so this is something that is the backbone of nowadays file system and database. Okay. And in the B plus tree, you can see that a node can consist of more than one values, and a node can have more than one child node. Okay, or more than two child nodes. Okay, for example, if we consider the left branches, okay, this branch, okay, we can see that this node has 3 child nodes. Okay, and this is something that is normal, okay, for B plus tree. Okay. So this is what you should know about trees. Okay, I understand that many of you have studied data structure this course, so you have understanding of binary tree and heap. Okay, but in fact there are far more different kinds of trees in data structures. Okay, and that is not able to be covered by the data structure course. Okay, and this is normal. This is actually normal. Okay, back in my days when I was studying in undergraduate. Okay, when I was in undergraduate student. Okay, I also just learn about binary tree and heap in the data structure course. Okay, I learned other kinds of tree in other courses. Okay, and that is normal. Okay, but I hope I can explain to you that trees, okay, there are many different kinds of trees in the data structure or computer science. Okay, it just doesn't have to be always to be binary tree or heap. Okay. So now let's get back to our lecture 3. Okay, so we are trying to conduct the search over this network. Okay, and now we need to think about something. Okay, when we are doing the search, we will want to keep track on what kinds of nodes that we have been searching so far. Okay, just like when you are deciding, okay, when you are deciding how the flow of a event should go. Okay, you may want to figure out some you may want to illustrate your decisioning in a organized fashion. Okay, so for example, if it rains, then I do something. Okay, if it doesn't rain, then I go into a window schedule. If it rains and the food doesn't arrive, then I will have another SOP to handle the situations. Okay, the standard operation. Okay, I have another ways to handle the situation. Okay, so if you gradually list out those different scenarios, you will actually form a tree. Okay, indicating your decisioning process. Okay, and essentially we are trying to do something similar in the search. Okay, we start off with a vector is the ACT. Okay, and for this city, this is the starting point of our search, so we also put it into the search tree. Okay, you should consider the search tree as a data structure to keep track of what we have been searching so far. Okay, and we start with the ACT. the ACT can travel to Cebu, Sirius, and Timisoara. Okay, so we will start our exploration. We will mark these 3 cities in our data structure to indicate that they are available, for our exploration later. Okay, so that is what we will do. Okay, so we add the Cebu, the Sirius, and Timisoara under the ACT. Okay, so after we add it under the ACT, okay, so from the structure we know that the ACT can go to Cebu, can go to Sirius, and can go to Timisoara. Okay, and we put this spin off is because back in the network, back in the state space diagram, the ACT can go to Sirius, can go to Timisoara, and go to Cebu. Okay, and we represent this able to go relationship back into the search tree by adding this 3 cities as the child node of the ACT. Okay, okay, and then we start our search. Okay, we continue on our search on these 3 cities. Okay, okay. Imagining the search tree is recording the possibility of the agent. It can go from ACT to Cebu. It can go from the ACT to Sirius. It can go from the ACT to Timisoara. Okay, so this search tree is storing 3 different possibilities that the agent can go to. Okay, it's storing the available actions that the agent can go to. Okay, so we pick one of them. We pick the Cebu because we don't know whether the Cebu can, because we don't know whether the Cebu going to Cebu will allow the agent can go to the end state. Okay, okay, but you may ask me, Professor, I have the whole map. So how come I cannot just know what path the agent should do to go to the end state? Okay, but here is a catch. Okay, this is a network. Okay, imagine this in your head. Okay, you have a MTR roadmap. You have an MTR system map. Okay, and yes, you have the map. Okay, but you still need to study. You still need to follow the railway in order to know what railway you should take in order to go from Mongkok to Tuen Mun. Okay, it makes sense, right? If I have an MTR system map, I cannot just take a look on it and immediately know that which railway I need to go. I need to take such that I can go from Mongkok to Tuen Mun. Okay, I cannot just take a look on the system map and I immediately know what railway I should take. I need to study the MTR system map and trace and then follow the railway line. Okay, to know that okay, if I want to go from Mongkok to Tuen Mun, I will need to first take the Tuen Mun line, and then I will need to transit to another railway, and then to the rest railway I can get to Tuen Mun. Okay, with the system map, even for human beings, if I am given the system map, I cannot immediately know what railway I need to take to go from one place to another with a blink of an eye. Okay, I need to investigate the railway that is available in the map, and I trace through the railway to know what direction I need to travel to. So this is the same here. Okay, although we have the whole state space diagram, without tracing through each possible route, I cannot know what route would get us to the conclusion, to get us to the goal state. Okay, so now we in the search tree, we are recording the AREC can go to Cebu, can go to Sirius, and can go to Timisoara. So now we start from Cebu. Okay, we imagine the situation that the agent chose us to go to Cebu. Okay, okay, does that make sense to you? And for Cebu, we further go back to the map and investigate. Okay, and when we further investigate, we know that the Cebu can go to Odeus, can go back to ACT, can go to February, and go to Remedial Vicha, okay? So these 4 cities are the cities that the agent can go to as Cebu. So we add these 4 cities back to the search tree. So the search tree is now recording what the agent can travel to where is the Cebu. Okay? The connections of Cebu to ACT to February to Odeus to Remedial Vicha. These 4 connections, this subtree is representing what is the cities that the agent can go to if it is at Cebu. Okay? Okay? So you can see this is how it is going, okay? We are gradually growing the search tree, and when we are growing the search tree, we are also encoding all the pathways, okay, between 2 locations in the map, in the network, okay? For example, we know that from ACT to Odeus, okay, in the search tree, it is travel to Cebu first and then to Odeus, okay? And this is concurrent, this is consistent with the transitioning that we have in the state space diagram. Okay, so essentially, when we are running the search algorithm, we are actually gradually exploring in the state space diagram, and essentially we are keeping track on the possible pathways of all the possible pathways between 2 points in the network in the search tree. Okay, okay. So each route between the wood node and the leaf node in the search tree is representing a path between 2 states in the search diagram, in the state space diagram. Okay, okay. So up to this point, any questions? Any questions up to this point? Any questions? So if we repeat this procedure, and if one day we reaches the goal state, okay, if one day we reaches the goal state, okay, then we can stop our search. And we can declare that we have found a path from the initial state to the goal state, because that path is already been included in the search tree. So imagine if we keep on going the search tree and suddenly the goal state become the leaf node of the search tree. Okay? Okay. Then in that scenario, because the leaf node is if the goal state becomes the leaf node of our search tree, and we know from the operation of the search tree, there must be a path from the goal state from the root node to the leaf node. Okay. The moment the goal state becomes the leaf node of our search tree, that is the moment that we found a solution that allows us to travel from the root node to the root node to the goal state. Okay. Okay. Then this is why we can use the search algorithm we shown here to solve the problem. Okay. Okay. The search tree is actually keeping track on what we are, what kinds of things, what is the path that we have explored so far in the state space diagram. Okay. Okay. So any questions? Any questions? Any questions? Okay. So now we have another issue. We know that the search tree allow us to keep track on the searching that we have been performing. Then the next issue is how we are going to implement the search tree. Okay. Okay. Just to do a brief recap, okay? The search tree is the data structure that is being created and being updated when we are conducting the search in the state space. Okay, idea concept of the state space search is that we start from initial state and then we try to generate, okay, try to generate all the pathways, all the path starting from the initial state. Okay, if one day, if a path that go from initial state to the goal state have been found, then we actually stop the search. Okay, okay. This is the core idea of the search algorithm we are working with. Okay, okay. But then there is a issue. First of all, the first issue that we are having is we have free node available for the ACT, right? From ACT we can go to Cebu, we can go to Cirrus, and we can go to TV Solar, right? And the issue we are having is choosing what node to explore first.
So we use the weighted sort of like which one has the lower cost that will run that.
This is one of the way, okay? And in fact, we can also choose which node will need to explore based on whether they appear in the search tree early or later. Okay, okay. So now let's consider other situations. Okay, for example, if we now explore the Cebu, okay, we have the ACT, the Factors, the Odes, the Visual Visa, the Cirrus, and the TV Solar. We have all these nodes in the search tree that is available for exploration. Okay, they are all leaf nodes, they are available for exploration. Then our question is choosing which one. We can actually go back to search Cirrus and go back to search TV Solar. And after these two nodes have been explored, then we start the second depth node for exploration. Okay, we first finish all the node one, the nodes with the depth one. Okay, we explore them first, and then we start exploring the node with the depth two. Okay, we go do it layer by layer. Okay, this is the first approach. Or we can go to explore the deepest node first. We go as deep as possible, and if that route doesn't allow us to go to the root node, then we trace back. Okay, okay. This is another approach we can also take. Okay, or the third way is that we choose the path, we choose the node that have the lowest path cost. Okay, that is the third way. So these three ways would actually contribute to three different algorithms. Okay, and the major differences is how we select the nodes. Okay, how we select the nodes for exploration. Okay, and the next thing we need to also discuss is how we implement the search tree in the first place. How we really write code for the search tree in the first place. Okay, so these are the two things we need to discuss in the notes. And also there is more examples about what will happen if we keep on exploring the search tree, and this is the search tree count, and we also show gradually the search tree will cover more and more region in the search space. Okay, okay. So any questions? Any questions? Any questions? Okay. And if we are talking about the implementation of the search tree, we would actually need to consider the following things. Okay, we would actually for a state, okay, the state itself is only a node in the search space. Okay, but when we are building the search tree, we also want to add additional information such that we can identify we can form the connection of the tree in the first place. Okay. So for example, okay, if you are considering the search tree, you have the children node, right? And the search tree, and for every node in the search tree, you also have the parent node, right? So you in the node, when you're designing the data structure for the search tree, you also need to keep the information of what is the parent of the node and what is the children of a node, such that you are able to maintain the search tree structures. Okay. If you do not have a object reference back to the parent node or to the children node, you cannot really keep the structuring of the search tree in your memory, in your computer, right? In your computer, right? I guess in data structure course you learn about that, right? In a binary tree, okay, I guess you have used to learn this, okay? In a binary tree, even that a node in the search tree, even that a node in the binary tree, that node should have object reference for pointing to its child node and its parent node, right? Right? In the data structure course, you learn about binary tree, right? Have you learned about how to implement a binary tree? Okay. Okay, so let's consider this. Okay, all these nodes are represented as a object in the memory. Okay, so in order for the node to know what is its parent node or what is its child node, you will need to make the node itself able to have the object reference, keeping track what is its children and what is its parent. Okay. Okay, such that you can really record this whole tree structure in the main memory. Okay, makes sense, right? Makes sense, right? Up to this point, makes sense, right? So when we are really designing the search tree in the implementation, we will need to add this information to the nodes. Okay, in our drawing, it is simple. When we want to indicate which is the parent, which is the child, we draw a line, right? We draw a line, right? This line is not something that can be represented easily in our computer. Okay, so instead of drawing that line, okay, in the main memory, we actually let the node recall what is its parent and what is its children, such that the node connectivity is recorded as the child node record and the parent node record of each node. Okay, okay. If I know, if for any node here, if I know what node is its children and what node is its parent, then it can always reconstruct the search tree. Okay. The lines in search tree is represented as the parent and children relationships, and the parent and children record of each node. Okay. Okay. Any questions? Any questions? Any questions? Up to this point, still able to follow, right? Okay. So we also want to keep track on the action, okay, that have been done, okay, such that we can generate the solution back. In the search tree, we didn't in the search tree we discussed that here. We actually don't mention about the action that need to be taken to go from the initial state to transit from state to state. Okay, but when we are implementing the search tree, we also want to keep this information in the search tree such that we can generate the solution from the search tree directly. Okay, okay. If you just record the connectivity, then I don't know what the agent has done to do the transition length, then that is not helpful for us. Because at the end, we want to know the sequence of action that allows the problem transit from the initial state to the goal state. And the sequence of action is what we really want. Okay, so we need to also keep the action into our recording, into our search tree data structures. Okay. 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 And we also want to know the depth of the node right now, okay? For the sake of knowing the for the sake of also knowing how long our solution is, okay? And at the end, we also want to record the path cost of the node such that we know how much cost has been taken to travel to a node. Okay? Okay? And at the end, you have implementation like this, okay? So if you take a look on our implementation right here, you will see that I created a object, okay? And this object is called the search node. And in this search node object, you actually found that I recorded the parent node, okay? In this search tree node, okay, maybe I'll make it bigger. In the search node, okay, the search node is the node object I created to represent a node in the search tree. And in the search node, you can see in the constructor that I shown here, okay, you actually can see the parent node, okay, that is a pointing device, a object reference that points back to the parent. I also need to have the action, okay. I also need to record what action that allows the agent can transit to a current state. And I also need to record the state represented by the node. And I also need to record the path cost and the depth. Okay, so that is why I define the search node in the search tree in this manner. Okay, okay. So any questions? Any questions? And you can see that the thing I talk about here is consistent with the description we have right here. Okay. And what we talk here is essentially how we implement it is shown right here. Okay. And you can also see that there are some extra functions. Okay, these extra functions are written there for the sake of implementation. Okay, one is to convert the the first one is to convert the states. Okay, the states is to convert the state into a string form such that it's easy to print out. And the second one is to define how two nodes is being compared. Okay. So any questions? I just define it to be true, okay, such that the comparison is easier. Okay. I just ignore I just disable the actual comparison between two nodes. Okay. Essentially, I just make sure that the one that is at the left hand side of the comparison is always smaller. Okay. Is more small. Okay. Okay. Something like this. Okay. So any questions? Any questions? So this is how we actually implement it. Okay. And the real operations of the search tree, okay, will be discussed at the Friday lectures. Okay. So if you want, okay, you can also take a look on the coding right here. Okay, if you want to self-learn, you can refer to the lecture notes. Okay, and to understand how the search algorithm works, how the search tree works, and you can also refer to coding here to understand how the actual search tree is being built. Okay, but anyway, I will go over all these notes in great detail in the Friday lectures. Okay, but if you are interested, you can refer to the code and self-learn. Okay, I always promote self-learning. Okay, and this is the end of today's lecture. I will actually end the recording right now, and